All right, folks, today we're going to talk about nutrition and training adaptations. Specifically, we're going to be talking a lot about signaling pathways, how those are going to be activated, how they work. At the end of the day, guys, just remember, it's just a flow chart. So, training adaptations are obviously the long-term changes we're having to our physiology, to our body, to our cells because of what we've done. So we can see based upon whether or not we do endurance style training or strength style training, we're going to see changes inside of the muscles and then throughout the rest of the body. So if we're looking over at the table, we can see capillary density. That's literally how many capillaries are feeding each individual muscle fiber. Goes up from endurance training, not from strength training. We're going to change up our energetic stores for things that are either anaerobic or aerobic. And we can see that between, obviously, we're going to increase muscle glycogen no matter what we do, but the amount of mitochondria, the density of those mitochondria, and so on, those are going to be influenced far more heavily by endurance training. And then the amount of energy related to anaerobic performance, so that's that ATP, PCR, glycolytic enzymes, and PFK, phosphofructokinase, is one of those glycolytic enzymes. That's going to definitely go up from strength training. But then we see when you get over to the oxidative system, we're getting a lot more from the endurance side of it, where we're increasing enzymes that are related to utilizing our mitochondria and the different citric acid cycle electron transport chain that's going to occur within of it, or inside of it. Then we get into our cardiac output, O2, and general amount of plasma volume, which is going to be aerobic changes. You're not really going to increase or really change your maximal heart rate from training. If anything, it might go down slightly. And we're going to find that our muscle fiber size, depending on what type of training we're doing, is going to go up or down. So what training does for these signaling pathways is create a signal inside the cell. The signal can be because of the stretch on the muscle, because of calcium being released from muscle activation, from different proteins being phosphorylated, such as AMPK, which is an indicator of energy availability inside of the cell. Now, once these get activated, they in turn are going to literally influence our DNA, and that our DNA is going to go through what's known as transcription. This is where we're going to create RNA. This RNA, ribonucleic acid, is then going to go ahead and leave the nucleus of that cell and move into the cytoplasm. It's there that it's going to be translated into proteins. And these proteins are then going to fold and then serve whatever function they need to in the body. So, for example, really hard training from both the calcium, the stretch applied, and other intramuscular damaging is going to cause our DNA, specifically for more actin and myosin, to in turn be transcripted, which is then going to leave as mRNA, which in turn is going to be translated into literally more actin and myosin, where we're going to increase our muscle cross-sectional area and our potential force production. So, we start this signaling cascade thanks to stresses that we apply inside of our cells. Okay? So, the example we have here would be the mechanical stress. So this would be literally the loading of a muscle, the damage done with heavier loads. This in turn is going to cause not just more calcium to be released, but also our cell to have a lower energy availability. So instead of having lots of ATP and ADP, we have AMP, which in turn is going to activate a certain kinase. And that's just an enzyme that in turn is going to activate other enzymes that are going to be related to translation and transcription inside of our cells. This in turn is going to give us a greater amount of genetic expression of whatever we chose, which in turn gives us the adaptation that we're looking for. Now, we utilize a wide variety of secondary signals in order to in turn get different changes to occur in the cell. The first one we're going to talk about is AMPK. AMPK is going to be activated by being in a lower energy state inside of the cell, meaning we don't have as much ATP, we're down with lower amounts of AMP. This is usually going to be activated thanks to aerobic style exercise. This in turn is going to cause us to use more glycolysis, so we are going to in turn break down more carbohydrates, because notice how we're blunting. You see the block arrows on glycogen synthesis and gluconeogenesis, because we're just trying to use it for energy. We're also going to be breaking down more fat and inhibiting activation of mTOR. And mTOR, the mechanistic target of rapamycin is going to be that protein that is the linchpin of muscle hypertrophy. Hence why high volumes of aerobic exercise inhibit muscle growth. Now, AMPK activation is then going to activate what's known as PGC1. PGC1 in turn is going to activate the genetic components inside of our mitochondria for our mitochondria to actually divide. So we literally have more mitochondria inside of our cell. Hence, we've got a bigger advantage when it comes to aerobic energy production. Now, when it comes to the mechanistic target of rapamycin, we're going to activate this through lifting weights where we do muscular damage, through nutrition, through things like leucine, or in the example to the right, we've got IGF-1 or muscle growth factor. This in turn is going to activate what's known as the insulin receptor 1 substrate, which in turn is going to activate phosphoinositol 3 kinase, and so on and so forth. Is at the end of the day, guys, you follow the flow chart. Now, AKT, which is not to be mistaken for AMPK, is going to inhibit FOXO and MRF-BOX, which are going to be related to inhibiting muscle growth. It's also going to inhibit tumor sclerotic factor 1 and 2, so that's that TSC, and our GSK3 beta, which when those are inhibited, we actively turn on more muscle anabolism, specifically by getting mTOR to interface with Raptor, which in then turn will phosphorylate P70S6K and 4 eukaryotic initiate or binding protein 1, which in turn is going to give us more translation of greater amounts inside of our cell of muscle, specifically the cross-sectional area. So the way this works is we have our primary signal, and this is going to happen over a course of seconds. This in turn is going to activate this signaling cascade, which is going to last for minutes, if not hours. In turn, this is going to increase our transcription and translation in our nucleus of the cell, and then obviously in our Golgi apparatus and our endoplasmic reticulum. This is going to last for not just hours, but potentially days. And then we get to protein synthesis, which if we're trying to build muscle mass, now we're talking about this is literally going to last for days. So an example, when we talk about mTOR and we're really trying to build muscle, this time course, after one hard training bout, you are going to have increased amounts of protein synthesis in those muscles for up to 72 hours after training. Hence why if your goal is to maximize muscle mass, you need to be training each muscle probably twice per week to maximize their size. Now, what's nutrition have to do with this? Well, it's going to actually help force certain changes. For example, how much glycogen we have is going to influence what we have to use more as fuel. So one of the concepts that we have from there is what's known as train low and compete high, meaning train with low amounts of carbohydrate and then compete with high amounts of carbohydrate. And what you're going to find is individuals that are training with lower amounts of carbohydrate and then they go and get higher amounts in for competitions, they're actually going to have a greater amount of aerobic performance because they've done a better job of relying on fats as fuel. So now when we add in extra carbohydrate, they've got extra energetic availability to enhance their performance. What we can also look at is some other things like changes, for example, like training on an empty stomach. Does that really enhance our adaptation? Some folks like to say that it's going to help more with fat loss. In reality, it's not really that big of a difference. Taking in carbs while we're exercising obviously is giving us an advantage energetically, but we're not forcing as much adaptation because we don't have as much stress on the body. Leucine is going to help with increasing intramuscular protein signaling, but that doesn't necessarily mean you're going to build more muscle because it's just one of the many essential amino acids. So it's the equivalent of saying, well, we know when we've got lots of mortar, we're ready to build a building, and we'll give them more mortar because that seems to get the masons there to show up, but they still need the bricks. They still need wood. They still need wiring. They still need door frames. They still need ceiling tiles, etc. So we still need everything in order to really enhance that performance. Now, when it comes to antioxidants, so this is taking things like vitamin C, vitamin E, what we covered previously in the class, it can be useful to supplement with that to decrease the amount of training stress, but in doing so, you're starting to blunt the body's endogenous production of those antioxidants, where you might not get as great of a training effect as you would have otherwise. And the same can be said about people that are taking NSAIDs. Those are the non-steroidal anti-inflammatory drugs like ibuprofen. And what those have been shown, when taken chronically, they actually decrease your total adaptation to your training, because we are actually blunting that natural inflammatory response and signaling that's going to occur in the muscles in order to enhance recovery. Now, we then have overtraining or overreaching. And this is going to be where we're applying more stress on the body in a shorter period of time than it can really handle. Now, what we can definitely tell you is if we're doing too much of it, specifically with aerobic stuff, we're probably not going to be fully maximizing our glycogen resynthesis, which means we're definitely going to decrease our performance. Now, the image I have below is an example of when we train. Obviously, our fitness, whatever area we're talking about, goes down because we're fatigued. We give ourselves enough time to recover in the red line, and we're going to slowly see our performance trending upwards. Now, if we keep applying stress and we don't allow for enough recovery for that individual, we're going to decrease our performance, and that's going to be in the blue. So, like anything else, these structures in our body, when we have damaged them, are going to require time in order so they can essentially repair the damage that's done. And if you apply it too frequently, we can really beat ourselves down. Now, glutamine is a preferred fuel that's utilized in your immune system, and it's definitely needed heavily in skeletal muscle. High dosage of it hasn't really shown to have any major positive effects on muscle anabolism and muscle size. However, it could potentially have a little bit of positive effect on decreasing risk of becoming ill when you're in periods of very hard overreaching, where you're actively trying to beat yourself down so you can hit a greater taper in recovery, but the research is still kind of out on that. Now, branched-chain amino acids can help potentially with delaying fatigue, was one of the arguments based on the central fatigue hypothesis and its competition with tryptophan going to the brain. And tryptophan serves as a precursor for serotonin, which is that kind of feel-good relaxation neurotransmitter. But same situation, it hasn't really been shown to have that type of efficacy to where it's going to really enhance our recovery or our performance.